This video describes the product and component choices I made for the CNC mill build, why I made them, and how much they cost. Product lists and spreadsheets showing costs will be available at the end of this video. Given all the possible component combinations and choices that are available to you for converting your mill, it would be mind-bogglingly boring to survey all of them. So this video is limited to the engineering trade-offs that I made to address space limitations, cost, available components, and my intended use cases. When planning your mill conversion, the most significant decisions that you have to make include what level of precision do you want versus how much can you afford to spend? What type of machine will you be converting? What CNC controller will you be using? The type and size of motors that you will use to drive the mill movements. The weight of the mill table or milling heads will determine the motor torque requirements. Let's take a moment to look at a couple of these in more detail. Starting with the controller board. The CNC controller board is the heart of your system build and handles real-time processing of the G-code that your CAM program outputs and tells the motors where to move the machine. The controller will allow execution of canned cycles that simplify operations like drilling bolt hole circles. Input signals monitor system activity and provide responses to fault detection generated by alerts from motor drivers, home and limit switch triggers, speed detection for spindles, etc., and probe trigger detection. Output signal control includes spindle speed and direction, motor motion, coolant operation, and probe enablement. There is a real-time operating system that drives the microcode for the controller board. In the case of my 3D printers, the equivalent would be Clipper or Marlin software on the printer control boards. So let's talk about the choices you have for motors and motor drivers. There are two basic approaches to motor design for CNC machines. Stepper motors are designed such that every pulse causes the motor to move a fixed angular amount. The angular movement is determined by the number of magnetic poles in the motor. In this example, each pulse will result in a 15-degree angular movement. A movement command from the CNC controller will cause the motor driver to deliver the correct number of pulses. The control for stepper motors is pretty simple. Typically, no feedback is used, so the stepper motor driver combination is relatively simple. Some features of stepper motors include that the motor will hold its position even across power failures. The motors are relatively low speed and only moderate torque, but they're pretty noisy. The biggest challenge is that stepper motors can lose steps. They are inexpensive motors, so really good for a relatively cheap build. Servo motors, on the other hand, fall into the category of deep magic. There are multiple types and implementations, but to keep it simple, the angle that the motor will move is determined by the length of the command pulse sent to the motor. This is known as pulse width modulation. In order to keep the motor movement correct, the amount of motion is monitored and is used as a feedback to the control logic. As a result, the servo drivers are much more complex than steppers. The servo motor is significantly more precise than steppers. However, they do not hold position without power. They tend to be higher speed and often have good torque capabilities spread across all speeds. Hookup of servo motors is much more complex and the drivers are much more complex. However, they are really quiet but pretty expensive. The CNC Cookbook website provides great information about motors and includes a spreadsheet for sizing your motor requirements, whether dealing with servos or steppers. This is a summary of the products that I opted for. The choice of mill was described in the intro video. In my case, a PM 728 VT. I purchased a double nut ball screw kit from Precision Matthews to simplify the mechanical conversion. An upcoming video describes the mechanical conversion of the mill. I opted for the Acorn board from Centroid. It is relatively cheap at $199. Most of the electrical connectivity requirements are taken care of for you. It has decent capabilities for a home machinist, including up to 4 axes of movement, and professional support is available. Centroid have added a relay board that simplifies connections rather than requiring a relay for each output control. This is the simplest of the logical wiring diagrams and will get you started on power and PC connections. There are specific wiring diagrams for various motor types and brands, and also diagrams that show how to handle e-stop, coolant, and many other options. The Centroid operator control software, CNC 12, runs on a dedicated PC. This includes all of the higher level logic and user interfaces. There is a free version available for hobbyists. So let's take a look at the Technic range of products that I bought. Technics provide a hybrid motor, where motor position is monitored and can be held over various fault conditions. The integrated motor driver handles the feedback loop, simplifying the connection back to the CNC control board. This is a look at the hybrid closed loop, and as you can see, the feedback goes from the servo motor back to the motor driver rather than to the Acorn CNC controller. Cost of Technic motors is not that much higher than steppers when you add in the cost of stepper motor drivers. The folks at Technic will work through your needs and make sizing suggestions. I opted for the ELS version, which gives enhanced positioning. This provides 6400 instead of 800 steps per revolution. I also opted to add a shaft seal to allow for flood coolant options. I purchased a pair of NEMA 23 servos to drive the X and Y axes. And I purchased a NEMA 34 servo to drive the Z axis. The IPC5 is a 75 volt DC motor power supply from Technic, because it handles issues like back EMF generated by the motion of the machine. The Power I/O 24 VDC is used to supply 24 volts DC for the Acorn CNC controller logic. I also opted for a Power 4 hub. This is a powered distribution board, which allows more flexibility with cabling and cable lengths, and provides the backup power for the motor logic. Technic provide cable pinouts and Molex connector requirements so that you can build your own cables. I started down that path, but there is a high overhead in crimping and testing all of those connectors, so I changed course and bought off-the-shelf cables. You need an additional 24 volt power supply for the Hub 4 and e-stop relay, so I opted for a generic power supply. One option I would recommend is the C86 ACCP board. It is an Acorn to ClearPath connector board that costs around $48 and simplifies all of the motor connections between Acorn and the ClearPath motors. So let's look at costs. A few things to be said about this build cost summary. As I said in the intro video, I needed a machine to work on projects like my Enigma machine and steam turbine blades, so precision is a high priority for me. My total came in at around $7,000, but you can certainly make choices that will drop $2,000 off the total price. If you have other options you prefer, drop them in the comments, but please identify what your goals were and if you might modify any of your choices now. This total does not include enclosures, coolant systems, work holding, tooling or probes, as your choice or substitutions in those areas will vary by several $1,000s. You may validly choose not to build an enclosure at all, or decide to skip the use of automatic probing. Costs for my enclosures and other add-ons will be covered in each of the specific build videos. If you would like a full costing of all components, drop a request in the comments. Links to the sources of my components are provided in the video description. Thanks for joining me on this series. The next video will look at the mechanical conversion for the mill. So of course, please subscribe and click the like and notify button to be informed when it is published.